This video is about the area under the line on a graph, A7. Now, as I mentioned in the video for A5, physicists draw graphs so that they can extract important information from the features of those graphs. Here is an example of a graph of power on the y-axis and time on the x-axis. Now, the equation that relates power and time is this equation here. The energy transferred is equal to the product of the power and the time. And on this graph here, you can see we have a straight line with zero gradient. At 1 second, the power has been 1000 watts for the entire duration of that second, and so the energy transferred is 1000 multiplied by 1, or 1000 joules. At 2 seconds, we have twice as much energy that has been transferred, and this pattern continues to increase. And what you'll notice is that 1000 multiplied by the duration is the area of this shape. 1000 is the y-axis difference, and 3 seconds is the x-axis difference. And those two multiplied together is the area of this rectangle in units of watt seconds, because we're multiplying a power in watts by a time in seconds. Well, 1 watt second is equivalent to 1 joule. So this is here 3000 joules, 3 kilojoules. And of course, by the time we get to the end of the 10 seconds, the amount of energy we've transferred is equal to 10 kilojoules. Well, that's fine if our graph shows no change in the value on the y-axis as the x-axis is changed. But what if the value on the y-axis depends on the value of the x-axis? So now you can see I've modified the graph slightly so that the longer that we have been using whatever appliance this is, the more power is transferred, and therefore the more energy is transferred. Now, if we were to just say at 10 seconds, what's the energy transferred? Well, that's 1000 times 10. That would clearly be incorrect, because we can see that we've been transferring less energy earlier on. What I'm hoping you can see is that now what we have is a triangle. So the energy transferred is the area of that triangle. We used this definition here of energy is equal to power multiplied by time, but we were clever when we drew our graph. We realized power was a function of time, and therefore we had to take the area under the line to find out the total energy transferred. We wouldn't just take two values and multiply them. The area of a triangle is half times base times height, and so this would be 10 times 1000, or 10 kilojoules, but then divided by 2, 5 kilojoules that's transferred. Now, I've modified the graph slightly, and you can see that when we first turn on this appliance, at time t equals 0, there is a power of 500 watts, and then the power increases linearly with time. So power is still a function of time. Well, how can we work out how much energy is being transferred in 10 seconds now? We remember that the product of power times time on a graph like this is the area of the shape between the line and the x-axis. There are a few ways of calculating the area. You can use the trapezium rule, in which we know the area of the trapezium will be equal to the area of the rectangle, where we take the value on the y-axis to be halfway between the maximum and minimum from the trapezium on the y-axis. So we have a shape like this, 1000 times 10, that's 10 kilojoules. Or we can divide this into two shapes, 500 multiplied by 10, so this is 5 kilojoules, and then we work out the area of this triangle at the top, which is also 5 kilojoules, and then add them together to get our 10 kilojoules. Or we can count the squares between the line and the x-axis. Now, this may take a while, so I'll speed up the process. This is 1, 2, 3, 4, 17, 18, 19, 31, 32, 33 and 34 whole squares, and all the other squares are part squares. Now, depending on your exam board, there will be different ways of counting part squares. There are two ways. Either you count every part square as a half square, no matter how big or small it is, or alternatively you count anything that's larger than half a square as one square, and anything smaller than half a square as 0 squares. I'm going to count these as half squares. So we're on 34. This is 34 and a half, 35, 35 and a half, 36, 36 and a half, 37, 37 and a half, 38, 38 and a half, 39, 39 and a half, 40. So this is 40 squares. Now the area of each square is 1 times 250 watts, or 250 joules. So that's 1 second times 250 watts, which is equal to 250 joules. So that's 250 joules per square. And when you multiply those together, you get your answer in joules, which is 10,000. Now you may think counting the squares is a pointless method of finding the area when you can just break the area down into shapes. And in a picture like this, you're right. However, if you have a curve, then you can't break it down into shapes. Perhaps you have a graph that looks like this, and we want to know the amount of energy transferred in 10 seconds. Well, we know that the energy is the product of the power and the time, but because the power is a function of time, we're going to have to find the area. We can't break this down into any sensible shapes or use the trapezium rule, so we'll have to count the squares. And let's do that. 1, 2, 3, 19, and then you'll have to make a judgment. Maybe this I'll count as 20 just because of how many squares here are more than half. It's difficult to judge, but we're making an estimate. I'm not including this little bit of a square at the top here, for example. So 20, and then let's add our half squares, and a half 21, and a half 22, and a half 23, and a half 24, and a half 25, and a half. So 25 and a half squares, and remember it was 250 joules per square in this case. And that gives us 6,375 joules. Now this is an estimate of the work that's done, but it's a good estimate, and it's the best one you're going to get with this particular graph. In the real world of physics, what we might do is try to find a function that matches this curve, and then we would integrate that function, but that is too advanced for A-level physics. In the sheet A7, and indeed A8 as well, which has further questions of this type, you will be asked to calculate the area and to say what quantity it represents, including a unit. And if you don't include the unit, your answer is incorrect. And depending on the style of graph, you will either be counting the squares, breaking the shape into other shapes, or simply using the trapezium rule. The choice is yours. But in each case, you start by looking at the quantity on the y-axis, looking at the quantity on the x-axis, and deciding what multiplying those two quantities together gives you. And to do that, you're just going to have to learn your equations.